Let's go ahead and solve this equation of the quadratic form that involves sines. So as you can see, when we take a look at this, it looks kind of complicated, and I know this throws students off pretty regularly, but we want to find all these values of theta that make true statements in this equation between 0 and 2 pi. I find that solving these down, what we want to do is we'd like to replace this and make it look like something we're comfortable with. So what I'm going to suggest is wherever we see a sine of theta, we're going to replace that with an x initially. So there's a sine of theta, there's a sine of theta. That first one is 2 multiplied by sine of theta squared. So because it's sine of theta squared, we're going to replace the sine of theta with an x. It's going to get squared. Next, we get minus 3 times, instead of sine of theta, x goes in that spot, with a plus 1 equals 0. Now, you don't have to do the substituting in if you're comfortable doing factoring, or maybe using the quadratic formula while still seeing a sine of theta involved. But a lot of students, if you can rewrite it with x's, somehow that makes it a lot easier as far as solving this down. I'm going to go ahead and suggest that we try to factor this one, because I think we can factor it. Maybe you have a different method for factoring this, but I'm going to suggest the AC method. All right, thinking ax squared plus bx plus c. So the first thing I'm going to do is calculate a multiplied by c. So in this case, it's 2 multiplied by 1, or 2 is the magic number that we're looking at. Now, there aren't many ways to factor 2, right? It's just 1 times 2. It's a nice prime number. But luckily, those two, if you add them together, because this is an addition, they add up to that middle number. We can make a 3 out of 1 and 2 added together. All right, so the AC method says this first term is going to come down, 2x squared comes down, and the last term comes down, the plus 1. And again, if you have a different way of doing this, I find the AC method is pretty hands-on. You can get good at it pretty quickly, but if you've never seen this before, it's going to look a little bit strange. We're going to rewrite that middle term strategically. We're going to use that 1 and the 2 as coefficients that we just picked out over here on the side. We have to make sure that because we now have like terms in the middle, if we combine those back together, they make that negative 3x from up above. So in this case, I believe we would have to have both of them being negative. So negative 1 minus 2 more x's makes negative 3x's. All right, we've strategically rewritten this, so now we have 4 terms. So we want to be thinking factor by grouping to proceed. So factor by grouping says you kind of group the first 2 terms together and say, hey, what do these have in common? Looks to me like they both have an x in common, right? There's an x and there's another x. So let's factor that out. By removing that common factor, we're going to need a 2x to produce that first term, and we're going to need a minus 1 to give us that second term. For factor by grouping to work, the second pair also has to have 2x minus 1 inside this set of parentheses. So a lot of times I write that out and then kind of work backwards and say to myself, what can you say they have in common? Well, they don't have much in common, but we can say they both have a 1 in common, and we have to make it a negative 1 so that if we redistribute, we get those same 2 terms back. All right, next, what we want to do is finish our factoring by saying what's out in front goes in one set of parentheses, and what's in common, what's in the same sets of parentheses in both of those, goes in the second set. So the 2x minus 1 goes in the second set. All right, from here, the rest of the solving, if this was just x's involved, would be x minus 1 equals 0, right? Set that factor equal to 0. 2x minus 1 equals 0. Set that factor equal to 0 and solve them down. So the first one shouldn't be too bad. We just add 1, move it to the other side. Maybe a couple steps here. We're going to add 1 and then divide both sides by 2. So it kind of feels like we're done, right? Yeah, no, almost. Remember that we kind of introduced x into this problem. Our original problem had sine of theta instead of x's. So again, what we're going to do is go back up here to how we defined x, and we're going to replace where we have x's with sine of thetas. So down here, instead of x equals 1, really we're going to use sine of theta is going to equal 1. And where x equals 1/2, it's going to be sine of theta is going to equal 1/2. All right, well, almost solved. Not quite, but we're almost there. All right, next thing I'm going to do is just kind of deal with these one at a time. When we have sine of theta equals 1, whenever I have ones or zeros or negative ones, what I like to do is think about our unit circle to help me out on this one. All right, the unit circle going around here, we define this to be whatever our cosine is going to be an x value for an ordered pair on the unit circle, and sine is going to be a y value for a point on the unit circle. So in our case, we're looking to figure out what point on our unit circle is going to have 1 for its y value. And I think we only have the 1 up here at the top, right? This point up at the top is going to be the ordered pairs 0, 1. So we have to pick out what's the angle that corresponds with going 90 degrees or going up here. Well, it's a quadrantal angle, and hopefully we have those memorized that has to be at an angle of pi over 2, thinking in radians. So in our case, the first one, we're going to get a solution here that our theta has to equal pi over 2. All right, that's the only time, the first time around the circle, that you're going to get a y value of 1. And remember, that's what we were looking for, only theta values between 0 and pi over 2, like the first time around. Okay, next, let's move over here to sine of theta equals a positive 1/2. So if we did a sine inverse on either side, what we would hopefully get back is we're going to get theta is going to equal pi over 6. You may also notice that 1 over 2, that ratio comes up a lot, that's one that hopefully we've memorized. That when you have sine of pi over 6, it always equals positive 1/2. Next thing I'm going to explore is which quadrant is pi over 6 in. Now I like the phrase, all students take calculus. All right, because what that reminds us of is all the different quadrants where our trig functions are positive and negative. In the first quadrant, all of our trig functions are positive, but then the next ones correspond with that first letter. Second quadrant, sine is positive, but cosine and tangent are negative. Third quadrant, tangent is positive, but sine and cosine are negative. And then finally, the fourth quadrant, cosine is positive, but sine and tangent are negative. All right, so in our case, we had sine of theta equals positive 1/2. Well, pi over 6 fits between 0 and pi over 2. So this is quadrant 1. All right, we got an angle in quadrant 1 of pi over 6. But there should also be an angle in quadrant 2 that also would make a true statement here, right? Because sine is positive, and we have sine equals a positive 1/2. We need one in quadrant 2. All right, so to get that quadrant 2 angle, what we need is a reference angle, right? As it works out that pi over 6 is in the first quadrant, that's automatically our reference angle. So let me label that a reference angle. Because that pi over 6 got returned, I'm going to use theta bar to represent that, is going to be pi over 6. All right, now to get an angle in the second quadrant, what I like to do is use that reference angle and draw it to the x-axis. All right, so we're going to start with pi, the x-axis, right, going that far around, and we're going to use our reference angle in here to back up from pi, right, to get an angle in the second quadrant. So really our end goal is find this angle that wraps around all the way into the second quadrant, and that'll be our other solution here. All right, so to get that angle, I'll call this one theta as well. All right, to find that value of theta, what we're going to do is start with pi, but then we have to subtract away whatever theta bar is. So in our case, this angle in the second quadrant is going to be pi minus pi over 6. Let's rewrite that with a common denominator. So that's going to be theta equals, we want 6 as our common denominator, so let's go 6 pi over 6, right? That's equivalent to 1 pi. Minus pi over 6, which is going to give us 5 pi over 6 for an additional solution. And that's all of our solutions, actually. We found the one in the first quadrant, where sine is going to equal a positive 1/2. We found the value in the second quadrant that's going to give you sine of 5 pi over 6 also gives you a 1/2. And then over here, we had found pi over 2 is a third value that's going to give you sine of theta equals 1. All right, so these are a little bit tricky in that you have to do a little bit of factoring along the way. You have to know about where things are positive and negative based on quadrants. But really, they aren't that bad. Take it one step at a time. If you need to do that let statement from the beginning to introduce x's, you certainly can, like I did. If you're uncomfortable with the AC method of factoring, use whatever method of factoring you're comfortable with. Not trying to force that on anyone. Want you to just have alternative ways to get through these problems and get to the right answers. So hope this helps out. Good luck as you're solving down these equations of the quadratic form with sines, cosines, and tangents.